thank the organizers for the invitation for me to speak here. Okay, so thanks. Okay, so what I want to talk about today is on the gonality and the hyperbolic geometry of a compact Riemann surface. We want to see how they are related. Okay, so this is a joint work with Professor Junmuk Hwang of KIAS here. Okay, so anyway, so let me start. Oops. So I will start with a compact Riemann surface. Okay, of genus G bigger than or equal to 2. Okay. So denote the canonical line bundle of X by Kx. Okay, so it's just the inverse of the determinant line bundle. So we call this a very classical fact that if the genus of the Riemann surface is equal to 2, then the canonical line bundle is not very ample. Okay, so so in other words, you cannot use sections of Kx to embed X into a big projective space. Okay. Now, on the other hand, if the genus is bigger than 2, then the canonical line bundle is very ample for general X, okay, but not all X. Okay, so for given G, there are always some Riemann surface X of genus G such that Kx is not very ample. Okay, and these are called the hyperelliptic curve. Okay, so in other words, X is hyperelliptic if and only if Kx is not very ample. And it's also well known that in this case there exists a 2-to-1 map, okay, from X to P1. Okay, so this actually characterizes hyperelliptic curves. Okay, and there's a corresponding hyperelliptic involution on X. Okay, when X is hyperelliptic. Okay, so and here I want to look at this last characterization for hyperelliptic curves. Okay, so if X is hyperelliptic, then there's a 2-to-1 degree map. Okay, and well, unless X is P1, in which case it's not. So if X is hyperelliptic, then the minimum degree of maps from X to P1 has to be at least 3. Okay, it cannot be 2. Okay, so for that, there's this definition here, okay, the so-called the gonality of a Riemann surface, which so I denote it by delta. Okay, so it's the minimum of the degree of non-constant holomorphic maps from X to P1. Okay, look at all these maps F and look at the minimum degree. Okay, that is called the gonality of X. Okay, so I denote it by delta X. So in other words, if X is hyperelliptic, then delta X is equal to 2. And if X is non-hyperelliptic, then delta X is at least 3. Okay. And what is known is that this gonality of a Riemann surface is always between 2 and G over 2 plus 1. Okay. You may have to put a round up here. Okay. And also, for each number in this range, okay, there are always some Riemann surfaces in the moduli space with the given gonality. So in other words, the stratum of Riemann surfaces with a given gonality in this range is always non-empty. Okay, so these are all classical known results. Okay, so for motivation, let's just recall this setting. So here we fix a compact Riemann surface X, okay, which is B mod gamma for some discrete group, okay, and so we now consider a sequence of normal subgroups of gamma, okay, gamma i's, okay, I from 1 to infinity, such that gamma 1 contains gamma 2, contains gamma 3, and so on, okay. And such that each gamma I plus 1 is of finite index in gamma I, okay, and such that the intersection of the gamma i's is the identity element in the automorphism group of B, okay. And now, so you're given such a sequence of normal subgroups, then you can get a tower of Riemann surfaces. Okay, so each xi is just B mod gamma I. Okay, so you get the tower of Riemann surfaces. So you can think of like x1 is at the base, and then you have x2 covering x1 and x3 covering x2, and so on. Okay, so at the top is just the B, the universal cover. Okay, so given such a tower of Riemann surface, then so let me recall a result of Keung, okay, which says that for such a tower of Riemann surfaces, okay, the canonical line bundle of xi is very ample, okay, if I is large enough. Okay, so in particular, it means that for a given tower of Riemann surfaces, the gonality of xi has at least to be 3, when I is large. Okay, so actually, Keung's result actually holds for towers of covers of quotients of bounded symmetric domains. Okay, so but let's just look at Riemann surfaces here. Okay, so now so with this result, okay, which says that the delta of the xi has to be bigger than or equal to 3 when I is large, then you can ask a very natural question. Given such a tower of Riemann surfaces, does the gonality of the xi's will be unbounded, or does the delta xi will go to infinity as I goes to infinity? Okay, Keung's result says that delta xi has at least to be 3, okay, if I is large, but it seems natural to ask whether delta xi will have to get bigger and bigger. Okay, so this is the first question here, and so I want to phrase the question in a more general term here. So here we start with a Riemann surface again, okay, X, and we endow X with the hyperbolic metric. Okay, so it's 4 dz bar over 1 minus modulus of z square. Okay, and then we denote the geodesic distance function on B by this dB. Okay, then we can define the injectivity radius of X, okay, which is just the 1/2 of the minimum of the distance between Z and those gamma Z's, okay, where gamma doesn't send Z back to Z. Okay, so this is the injectivity radius. And then to ask the question in more general term, you can then ask, can one here find an upper bound of the injectivity radius in terms of the gonality of the Riemann surface? Okay. So here by upper bound I means so here the point is that we want an upper bound which is independent of the genus. Okay, just an up. We want to say the rho x is less than or equal to some quantity just in terms of delta x. Okay, okay, for all Riemann surfaces and for all genuses. Okay, for all G's. Okay, and if you can answer this question, then you can answer question 1. Okay, if you answer question 2 affirmatively, then you can answer question 1 also affirmatively. And the reason is that for a tower of Riemann surfaces, what one can easily see is that the injectivity radius of the xi's has to go to infinity as I go to infinity. So in particular, if we have an inequality like rho x is less than or equal to some delta x, but if some expressions in delta x, but if rho x gets bigger and bigger, then it will also mean that delta x has to get bigger and bigger. Okay, so what one really need is to answer question 2 only. Okay, so well, so for in the case of hyperelliptic curves, okay, so when delta is equal to 2, Katz and Sabourin gave such a bound, okay, a non-trivial bound. Okay, well, of course, yeah. So so there they used the very specific fact that for hyperelliptic curves, there is this hyperelliptic involution. Okay, and using that, you can actually give such a bound when delta is 2. Okay, or what they actually get is well, I should say non-trivial bound for the injectivity radius of hyperelliptic curves. Okay. Okay, but first you might ask why this is a reasonable question. Okay, now for me as a geometer, I would say this is reasonable because to me at least, okay, to some extent, both the gonality of the Riemann surface and the injectivity radius are related to the positivity of Kx, okay, the canonical line bundle. Because, well, for delta x is the minimum of the degree of maps from x to P1. So if the genus is, well, if the genus is small, okay, when the Kx is negative, okay, then in that case the delta x is 1. But for when genus is 2, Kx is of degree when genus is 1, Kx is of degree 0, or even when then in that case delta x is also 2, and for gen equal 2, delta x is also 2. Okay, but then for higher genuses, delta x, at least for general x, gets bigger. Okay, so delta x surely is related to the positivity of Kx. And likewise, the injectivity radius is also related to the positivity of Kx. For that, let me just give a O result of mine and Huang. Okay, so here we let x be okay. Let me recall some definitions first. So here, let x be a compact complex manifold. You take a point x, and then you look at the blow up of x at little x. You call it so f. Okay, so f from y to x is the blow up, and denote the exception divisor by e. Okay, then some years ago, Desmailly defined this Sassagri number or Sassagri constant of a line bundle, or in this case the Kx. Okay, at a point x. To be given by the supremum of all those real numbers, epsilons, such that you pull back the Kx to the blow up, okay, and then minus epsilon times the exception divisor. You want this class to be NEF, okay, numerically effective over the blow up. Okay, so here it means you dot with any curve in y is beginning with 0. Okay, so you take the supremum of these epsilons. For which this is still true, okay, and you call this the Sassagri number of Kx at the point. Okay? You can globalize this, okay, by taking infimums over points x in capital X. So this number is a sort of a measure of the positivity of Kx. Okay, so the idea is that if that by pulling back and introducing this term, you decrease the positivity of Kx near the point x a little bit. Okay, but you cannot. Well, how much you can do that is really measured by this Sassagri number. So basically, this Sassagri number is a measure of the local positivity of Kx. Okay, so
you assume Kx is ample in X.
Okay, yeah, you assume it's ample. Yeah. At least for our interest, it's always ample. Yeah. Yeah. Okay. So so some years ago, Huang and me generalized a result of Lasser's-Well, okay, which treated the case of ample line bundles over abelian varieties. Okay, so we actually using Lasser's-Well's approach, okay, and we consider the case of quotients of bounded symmetric domains. Okay, so here we let x equal to omega mod gamma be a bounded symmetric domain. Take a point x. in X, then one can find explicit constants, okay, Z1, Z2, and Z3, depending on omega, such that the Sassatry number of Kx at any point X is bounded below and above, okay, by some constant C1 times hyperbolic sine square of another constant times the injectivity radius, okay. And for the corresponding upper bound, you can replace this injectivity. You just replace this injectivity radius by the diameter of X, okay. So let me not define it here, okay. So in the case when omega is just the unit ball in Cn, you can actually take C1, okay, to be just n plus 1, and C2 and C3 to be 1, okay. So so here, if you look at the first inequality, it just says if the injectivity radius is large, then this local positivity of Kx is large. So in other words, this sort of justify my claim earlier that the injectivity radius is related to the positivity here, okay. Actually, I will come back to the proof of this theorem later, okay, because I will need that. Okay, so okay, so now let me state our result here, which is actually just a affirmative answer of question 2, but I will state the result as some kind of volume inequalities. Okay, so so here we again let X be a compact Riemann surface of genus bigger than or equal to 2. We denote omega X to be the hyperbolic Taylor form on X. And now we look at this Cartesian product, okay, X cross X, and endow it with this product metric. Okay, so it's just you just pull back, take the sum of the pullback of the hyperbolic metric on each factor, and then you look at the diagonal, okay, D, okay, which are just those points x y where x is equal to y in the Cartesian product X cross X. You look at the diagonal, and then now so for each R, you consider a tubular neighborhood of the diagonal of X cross X. Okay, of the diagonal, you consider tubular neighborhood of the diagonal in X cross X. Okay, WR. Okay, which are just those points x y in the Cartesian product, such that dxy is less than R. Okay, so of course it contains the diagonal. So the picture is simple. So here you have X cross X. Okay, you have X cross X. So you have the diagonal. Okay, so X, and now you take so schematically you take a tubular neighborhood. Okay, so this is WR. Okay, so you take a tubular neighborhood like this. And you can actually, in a similar way as before, define the Sassatry number of the canonical line bundle on the of X cross X along the diagonal, not at a point, but along this subvariety, this diagonal. Okay, to be such that to be the supremum of k x cross x minus epsilon d, for which such that this is still nav on X cross X. Okay, here there's no blow up because we are just looking at the X cross X, which is 2-dimensional. D is 1-dimensional, so you don't need to blow up. Blow up or not of a hypersurface is the same. Okay, so you don't need to blow up, but you can still define this to be the Sassatry number. Okay, so and oops. Okay, so the statement I want to state here is that so if R is small enough, okay, R is less than the injectivity radius, then you take any one-dimensional complex analytics of variety V in this tubular neighborhood, okay, say intersecting the diagonal, okay. Then one has this volume lower bound. The volume of this analytics of variety will be bigger than or equal to 8 pi times hyperbolic sine square of r over 4 times the intersection number of v dot d. Okay, so here you take any subvariety v, okay, which intersect d at a certain number of points, and then you want to get a lower bound of the v with respect to the product hyperbolic metric on x cross x. Okay, so this is the lower bound. Okay, and remember, well, of course, omega x cross x is related to the first transform of kx cross x. So it's actually a transform of kx cross x. So you can actually translate this easily into this statement about the Sassagri number, namely that the Sassagri number of kx cross x along the divisor d, along the diagonal d, is bigger than or equal to 4 times hyperbolic sine square of x over 4. Okay, and this inequality actually is sharp. Okay. In a sense that is realized by these so-called anti-diagonals. Okay, it's quite obvious what they are. Okay, so given upon x, okay, you just take the local. You just look at the graph. You take look at the graph of the local symmetry of x at a little x, okay, and yeah, it's better to draw a to draw the diagram here. So the anti-diagonals are just this, okay, just this, okay, intersecting. Yeah, they are themselves. Yeah, so it's just this, okay. This is the graph of the symmetry of x, a little x, okay, and okay, so these are sharp inequalities. Okay, and now once you have this result about this Sassagri number of kx cross x along d, then immediately you will get the answer to question 2. Okay, so a corollary is that you start with a Riemann surface of genus G bigger than or equal to 2 with Gonality delta. Then the injectivity radius rho x has to be less than or equal to 2 times inverse hyperbolic cosine of G delta over G plus delta minus 1, and of course. G over G plus delta minus 1 is less than or equal to 1. So in particular, this is less than or equal to 2 times inverse hyperbolic cosine delta. Okay, and so what we actually get is an upper bound of the injectivity radius in terms of delta, without involving without involving the genus G. Okay, now in particular. If rho x goes to infinity, then definitely delta x will also have to go to infinity. Okay, so in other words, if the injectivity gets bigger and bigger, then delta x will also get bigger and bigger. Okay, so okay, but let me just first deduce corollary 3. From theorem 2 first. Okay, it's actually very simple. Okay, by the very definition that of the Gonality, it means you have a map f from x to p1 of degree delta. Okay, and now you just look at the graph of f, and then you put back to x cross x. So in other words, you look at this curve gamma, which is just those points x, and then f inverse of f of x. Okay, so you look at this this curve gamma, which comes essentially is from the graph of f, pulling back to x cross x, and you can easily compute the class of gamma, which is actually equal to delta over 2g minus 2 times k x cross x minus d. Okay, that is easy to see. And now remember we know that kx cross x minus f minus a certain number times d is numerically effective. So in particular, you just let that class intersect with this curve, okay? Intersect with this curve, and then you can get an inequality, which is just this precisely. Okay, so so since we know that this is numerically effective, so you let it intersect d, intersect gamma. We know it has to be beginning with 0, but on the other hand, both gamma and this class, they are all in terms of kx cross x and d. Okay, but one can easily compute what d dot d is 2 minus 2g. What kx cross x dot d is 4g minus 4, and what is kx cross x square is 8 times g minus 1 square. Okay, so you just plug this in, and then you get the inequality. Here I have written this as hyperbolic sine square, but you can use the double angle formula and convert it into an inequality involving hyperbolic cosine. Okay, so this really just comes from the intersection. Okay, and as I mentioned before, in particular, if you have a tau of Riemann surfaces, then since the injectivity radius will go to infinity, so delta x will also go to infinity. Okay, so that answers 1 and 2. Okay, so what I want to do in the remaining time is to look at the proof of this volume inequality. Okay, the proof of this volume inequality. And for that, I actually have to go back to the proof of theorem 1. Okay, theorem 1 is the lower bound. Is the lower bound of the Sassagri number for kx. Okay, so let me just recall briefly the proof of this inequality. Okay, that the Sassagri, in the case of a portion of a bounded symmetric domain, the Sassagri number of kx at the point x is bigger than or equal to c1 times hyperbolic sine square of rho x. Okay, so let's recall briefly the proof. Okay, so for that I have to recall another definition, another characterization of the Sassagri number, okay, in terms of singular matrix. So here, let's denote by C plus of kx at the point x to be the class of this singular locally integrable Hermitian matrix of H, H of kx, okay, which was moved away from the point x, okay, and such that C1, the first term form of this H is beginning with 0 as a current, okay. So its local is given by possibly a singular pre-subharmonic function. Well, it's singular only at the point x. Okay, otherwise it's smooth. Okay, and if you write H as e to the power 2 phi h locally, then by Derma E, we know that actually the Sassagri number of kx at the point x can also be characterized as the supremum of the Lelong number of the phi h at x, okay, where h varies over you take the supremum over all these singular Hermitian metrics of positive curvature. Okay. So the Renault number, remember, we call that is just the lim inf of the function phi h over log of modulus of z minus x. Okay, and you let z go to x, and you take lim inf, and then that's the Renault number. It's basically the pole order, okay, of phi h. Okay, so so using this characterization of Sassagri number in terms of singular metrics, you so to get the lower bound of the Sassagri number, all you have to do is to construct this singular Hermitian matrix of positive curvature, singular at a point, and such that the pole order at the point is as big as possible. That's all you need to do. So okay, so what you do is you just start with the canonical Hermitian metric H0 on Kx, such that its first term form is omega x. Okay. Then, so here you take a you look at this geodesic ball, and this is the point x. So here then you well, so in this geodesic, so for this geodesic ball, it's just a Euclidean ball, okay. So it's, in particular it's just a Euclidean ball. So okay, so this is b x rho x. So what you do is you take the you look at the Batman metric, the Batman kernel function. Okay, so H0 actually can just be given by the Batman kernel function. Okay, and the k zc. Okay, and then so on this ball, on this geodesic ball, omega x is just given by I dd bar of phi h. Okay, so phi h is log of this Batman kernel function. And now all you have to do is to modify this Batman kernel function on this geodesic ball, okay, which is a Euclidean ball, and then you keep the metric away from this ball unchanged, but then you modify the metric of kx, or modify this Batman kernel function in this ball, okay, such that it becomes singular at the center, and then with a pole order as big as possible, okay, at the center, okay. So how do you modify this? Is actually very simple and elementary, just by direct modification. Oops. Okay. Oops. I will go back to this modification later. Okay, but. That is the whole scheme. Okay, it's very simple and straightforward. Okay, so now let me then go to the proof of theorem 2, the volume inequality for subvarieties near the diagonal. Okay, so this time the difference is that instead of a point, you're dealing with this diagonal. Okay, and so of course you might just want to use the similar approach, okay, and get the Sassagri bound for kx cos x minus for kx cos x, okay. For the, you want to get a lower bound of the Sassagri number of kx cos x near the diagonal, with respect to the diagonal, rather than with respect to a point, okay. So you just want to modify the proof. So if you want to use the scheme as before and try to get this lower bound of the Sassagri number, what happens is that in the case of Sassagri number with respect to a point, as you see before, we have this potential function, okay, for omega, for the hyperbolic Kähler form, such that for the Batman metric, and it's a potential function, okay, on this geodesic ball, okay. But and then you modify this Berman kernel function, okay. But on the other hand, if you want to do the same thing for this tubular neighborhood near this diagonal, then there simply doesn't exist a potential functions for omega x cross x in this tubular neighborhood, because for the obvious reason that if you can write omega x cross x as IDD bar phi on this tubular neighborhood, it means this is this function. Well, this is positive definite, so it means this function phi is strictly pre-subharmonic on WR. But definitely you cannot have a strictly pre-subharmonic function on WR, because it contains this complex variety. Okay, necessarily any pre-subharmonic function has to be constant along this diagonal. So it cannot be equal to. So this cannot be equal to something positive definite. So what we have to do is then to modify this approach, and instead of getting a potential for omega x cross x on this tubular neighborhood, we have to settle for slightly less, okay, but still enough for our purpose. So to overcome this, what we do is we construct an auxiliary, still smooth, okay, potential function mu, okay, on this tubular neighborhood, okay, such that IDD bar mu is bigger than equal to 0, but it's not equal to omega x cross x, but it's less than or equal to omega x cross x, okay. So we settle for an inequality instead of an equality, okay. And now well, to how to construct this mu is not difficult, okay, but it's easier to write it in terms of the universal cover, okay. So oops. Okay, so here you look at you look at gamma, and you look at this B cross B, okay, and then look at you look at the diagonal embedding of gamma in gamma cross gamma, okay. So J little gamma is just gamma, okay, in this diagonal embedding, okay, in the automorphism group of B cross itself, and then you can define a similar tubular neighborhood in the universal cover, okay. So you can define WR tutor to be those points Z and W in the product B cross B, for which the distance between Z and W is less than R, okay. You can write in terms of explicit coordinates. And then if R is small enough, then this WR is just given by this WR tutor modeled by this J gamma, okay. So and then you on B cross B you can look at this essentially the distance function, okay, composed with this hyperbolic tangent square, okay. So chi tutor of ZW is just W minus 0 over 1 minus C bar W modulus square, okay. So essentially you look at this this function, which comes from it's natural function, okay. It's quite natural. I hope it's natural to all of you, and then it will descend to a function on W R or W rho x, okay. So it's just hyperbolic tangent square of the distance between x and y, okay, over 2. Okay, so now so for example, using this chi, you can construct a lot of auxiliary functions, okay, auxiliary potentials. So you can let, for example, F0 to be minus log of 1 minus t, and then you let the mu naught to be F naught composed with this chi, okay. Then you get a function on WR, okay. And then you can check directly. This function actually satisfies that is pre-subharmonic, and then is less than or equal to IDD bar of mu naught is bigger than or equal to 0, but less than or equal to rho x cross x. Okay, so this is one auxiliary function that you will get, but but it will not be optimal. Okay, you will not get very good. You will not get the sharp inequality that we want. Okay, but so for optimal results, we actually need to modify this this mu 0 to some mu. Okay, and in the proof, you actually see that this you actually to get optimal result, you want the mu to be such that so you write mu as f composed with this chi. Okay. And for optimal result, you want f prime, okay, the derivative of f, to be as big as possible. Okay, that is the condition for optimality. And in fact, so here you can write your function f as the integral of some function phi over 1 minus r. Okay, so for f prime to be maximum. To be maximal, you actually want phi to be maximum, okay, to be maximal, and also for example, the condition that you want dd bar mu to be bigger than 0. Remember, mu is just f composed of chi, okay. Then this condition is equivalent to that phi is positive, phi prime is also positive, okay. And remember, we also want this auxiliary potential mu to be such that dd bar mu is less than or equal to the omega x cross x. And this actually will also translate into some inequalities, okay, some differential inequalities. And okay, so finally, to get this phi, what you do is actually you just set some of this inequality. So actually, you set this last inequality equal to an equality. Okay, you solve, and then you can solve the corresponding equality, and then you can get the phi. Okay, and it turns out this phi will satisfy all these conditions. And in fact, it turns out this is also the optimal one, okay, the biggest. Remember, we want phi to be as big as possible, so it turns out this is also the biggest possible, okay, for each t, okay. So, and then after you integrate, you get this f, okay, you get this f. So, okay, once you get this auxiliary potential, then the rest is not difficult, okay. So now you can once you have this mu, okay, this auxiliary potential on this tubular neighborhood, you can start to modify this mu, okay, so that it becomes singular, and then with singularities along this diagonal, okay. And then one can then compute the Lorentz number of the modified function along this along the disks, okay, perpendicular to along this kind of disks, okay, orthogonal to the diagonal, which will turns out to be bigger than or equal to 8 times hyperbolic sine square of r over 4, okay, up to some epsilons. And how do you modify this? It turns out it's easy. Okay, it really comes from a simple lemma. Okay, let me just state the lemma here. Just that you start with two given number a and b positive, s not less than 0. Then we can find a function, okay, from a real value function from defined from minus infinity to s naught, such that at S0 its value is given A, and its derivative at S0 is the given number B. And moreover, you can make sure that phi is always positive, and phi prime is also positive, and hence the limit of phi as s goes to minus infinity is just a minus epsilon. You basically just flatten out the function. Okay, keeping the picture is simple. Okay, so you just you prescribe the derivative at a point and the value of the function at a point, and you just want it to be very flat, but still always increasing. But then at infinity, at minus infinity, the function just decreases a little bit. It's easy to construct. Okay, so let me just okay. So once you have this, then essentially you just so now you now look at this V. Okay, at this V which intersect D at a number of points. Okay, and then you compute the volume. So the volume of V is just the integral of V with respect to this volume form. But now you have this auxiliary potential, so it's bigger than or equal to the integral of V wedged with this mu. But then you use Stokes Theorem, and this is equal to the integral of V wedged with mu epsilon, I to the power of mu epsilon. But mu epsilon is singular, and then we know the pole, more or less. We know the pole of mu epsilon along D. So so it's bigger than or equal to this 8 hyperbolic sine square of r over 4. Okay, so essentially it's just Stokes theorem. Okay, and for this you just use a certain projection argument. Okay, so this is the proof actually. So in the remaining 10 minutes or so, I want to look at this some corollaries. Okay, so here we want to look at this T invariant. Okay, which is this invariant Tx, which is used in the study of ample Keung over the symmetric product of Riemann surfaces S2x. Okay, and they did not write it in this way, but it's equivalent to this. Okay, so you look at Tx, which is just 2g minus 2 over this Sassadri constant Sassadri number kx cross x with respect to D, again, and then minus 1. Okay, now so what is known is that Tx is always less than or equal to g, and that Tx is less than or equal to g minus 1 if only if x is non-hyperelliptic. Okay, so Busasana construct a sequence of compact Riemann surfaces xi, okay, such that as I goes to infinity, gi go to infinity, of course, okay, and then the injectivity radius of xi is at least 2/3 times log of gi, okay, minus some fixed number c1. Okay, so they construct. So essentially, they construct a sequence of Riemann surfaces with big injectivity radius. Okay, so using the Busasana sequences and also the theorem 2, okay, this Sassadri band of kx cos x with respect to diagonal, you can actually get a result which says that you can find a constant c and a strictly increasing sequence of positive integers gi and corresponding non-empty open subsets ui in the moduli space of Riemann surfaces of genus gi. Okay, such that on this UI, for each Riemann surface corresponding to points in this UI, the Tx is less than or equal to C times Gi to the power 2/3. Okay. And if you compare this corollary with this theorem of Kouridakis, which says that for very general x, the Tx is less than or equal to G over essentially square root G. So it's Tx less than or equal to essentially square root G. Okay. For very general x, but here this corollary says on the Riemann surface you can find a Euclidean open set for which at every point the Tx is at least Gi to the power 2/3. Okay, so this is not quite optimal. Okay, for optimal, you expect this to be 1/2, this exponent to be 1/2. Okay, so it seems natural to ask this question. Can one construct a sequence of compact Riemann surfaces xi for which the injectivity radius of xi grows like a log of Gi minus O of minus some lower order terms. So Busasana's examples says that there exists such a sequence of Riemann surfaces with injectivity radius growing like 2/3 times log of Gi. Okay, so my question really is whether you can improve it, get bigger injectivity radius. Okay. So that this constant, instead of 2/3, it becomes 1. If so, if you can do that, then this corollary 5 can be improved, so that this exponent is like 1/2. Okay. So yeah. So this is something I don't know. Put it in another way, given a G, okay, does one know what is the biggest injectivity radius of the Riemann surface for Riemann surfaces in the moduli space? Okay. Yeah. Given a G, do you know what the biggest possible injectivity radius of the Riemann surfaces are? Okay. Yeah. So that's the question I want to raise here. Yeah. Okay. Finally, let me talk a bit about the non-compact case. Okay. So here, so what I have presented earlier is from more a geometric approach to study this gonality, but actually there were some works on this gonality using spectral theory. Okay, so let me just record this result of Abramovich. So here you let gamma n to be the principal congruence group, okay, consisting of those 2x2 matrices congruent to identity modulo n, and you take a congruent subgroup. Just means gamma contains some gamma n. Okay, for such a gamma, you look at the H mod gamma, you get Y gamma, and then you add, you just take the compactification of Y gamma by adding by adding a point to each cusp. Okay, so you get this X gamma. And so what Abramovich proved was that the gonality of this compactification of Y gamma is bigger than or equal to 7/800 times the index of gamma in PSL2C. Okay, you can replace this by just the genus. Okay, so it's so in other words, in this case of congruent subgroups, the gonality of X gamma is bigger than or equal to some linear expression in the genus. Okay, and so of course the case of gamma is a very nice. I mean, for such arithmetic cases, a very nice, we are looking at very nice discrete subgroups. Okay, and in this case, one actually gets a pretty good lower bound of the gonalities in terms of the genus. Okay, and for that he used some results on the lambda 1 of X gamma. Okay, if you can improve this, you also can improve this bound. Okay, so this is the approach from spectral theory. Okay, and yeah, what I described earlier is more from more geometric point of view. Okay, so I think I will stop here. Yeah. So yeah, let's just say the whole question I want to ask is really, oops. Okay. Is that's a question I want to know very much. I mean, what is the given a G? What is the biggest injectivity radius of a compact Riemann surface of genus G? Okay, that's. Huh? Yeah, right. But what is the biggest possible? Yeah, of course, there's a natural bound for the injectivity radius in terms of the area. Yeah, Gauss-Bonnet. Yeah, essentially, right. Yeah. I want to know the exact. Yeah, whether you can really how good you can approach to whether you can construct sequences of. Whether you can construct Riemann surfaces whose injectivity radius is quite close to what you will get from the Gauss-Bonnet. Yeah, that's my question really. Yeah. And Busa-san, give some constructions which are pretty close. Well, not exactly very close, but yeah.
So for general manifold,
Yeah.
the point is you need to construct a Fourier subharmonic function with the biggest with one singularity and with the biggest possible number. That's what you want to need to construct for the Riemann surface. Right? Just you want to construct
For Sassagri number of the kx or kx cross x. Okay, for the gonality problem, what we need is a lower bound of the Sassagri constant of kx cross x with respect to the diagonal, not just a point.
Okay.
Yeah.
So construct a Fourier subharmonic function that has singularity along the diagonal.
Right.
With the biggest possible.
Right. Yeah. That is the approach here. Yeah. Versus this. Versus the other approach, which is more from by getting a bound on lambda 1. Yeah, that's why we did this volume inequality. They are equivalent. Yeah.
Can you show the last page?
Yeah, sure.
Here, the last slide.
Yeah.
Lambda 1
Of X gamma is.
first eigenvalue of
Yeah.
X gamma or Y gamma?
Sorry, it's Y gamma, I think. Yeah, Y gamma. Yeah, you're right. It's Y gamma.
So your result for the complex case was related to the first eigenvalue?
I'm not sure. Well, I'm not sure.
And why here it is related to the first eigenvalue?
Yes, yeah. I'm not sure. Okay. You mean whether I can get some results on lambda 1 by from our volume inequality? I haven't thought about that. Okay. It may be. I don't know. I mean, I haven't thought that carefully. Yeah. It may be. I mean, I don't know.
You
But-
told that we could improve some bound for lambda.
Yeah, right. Then you can, yeah, at least then you can improve this bound on the gonality, the lower bound of the gonality.
So the conjecture is lambda 1 is greater than or equal to 1/4.
Yeah, that is there are all this a lot of results on this, right? So I think he did this in the mid-90s. That time it's like 0.21, I think. Yeah. So I mean, I don't know. Yeah, the two approaches should be related. I mean, they all give you information on the gonality. So, but I don't know how exactly they are related.